Hello, everybody. This is 7:30 already, and we need to start with our discussion tonight. Hope you have a good weekend and ready for uh, picking up more challenging topics in the computer architecture. So, this is the second part of the pipeline architecture, and specifically, we discussed here about the data hazard and the control hazard and how to mitigate those problems. Any specific questions, concern on that topic or anything else, let me know. I don't see any question on the discussion either. I hope you guys have went through all those lectures, videos, and slides. So I want to discuss, not discuss really, explain a little bit more onto this control hazard and what plays around in terms of this five-state machine. Let's do that. So if you go to my whiteboard, I have already given drawn some pictures around for that example. And it's a simple program which basically talks about like increment some register and then do some addition on top of that, and then compare that R1 register with R4 register. And if they're not equal, it goes back to jump to this instruction, repeat this whole loop. And then from there, once the loop is done, it goes forward and proceed with the other instruction. That's the intention of this program. Now let's see how it plays out in our pipeline uh, architecture, right? Remember, pipeline, it tries to uh, like execute these instructions in parallel, uh, and then we'll see, like, if we want to execute them in parallel, what kind of hazard comes up at this instruction, like, which is kind of a control hazard. And let's also assume there is no data hazard or data hazard has been mitigated. So that's not a focus of this discussion. We solely focus on this control hazard scenario. We also assume this is a predict non-taken. Predict non-taken means at this point, processor thinks that it will come out of the loop and proceed to the outer part of the loop. That is the predict not taken. Branch is not taken. It just fall through this natural course. So that is the predict not taken assumption. Any questions so far before I start there? Okay, now let's see, right? So we start this program execution, and let's say at that point, we have these R1 values stored at 17, R2 at 10, R3 at 10, and R4 register at 25. So what happens at this point, your instruction machine will fetch this instruction, right? This instruction. That means essentially your memory is accessed, instruction memory is accessed for your first instruction, that the one which is being fetched. Now next clock cycle, this instruction will move to IDRF phase. That means this specific instruction is reading from the register file if needed. And then this instruction will be fetched. This is fetched by the machine in the pipeline architecture scenario. And then next clock cycle, this guy will move here, or let me just put the resource flag. This one. Okay, so this instruction is instruction memory being accessed. Okay, now next clock cycle. This one moved here. That means this is now to be used ALU if needed. This moved to IDRF, so this guy will start accessing registered file, and BNE is accessed. So BNE is accessed from the instruction memory. Now next clock cycle, this guy will go into the mem state. This one will come to the exe state. This one will come to the IDRF. And now what would happen? What to fetch from this point? See, like at that point, at this point, at this instruction, after that, what should we decide? Which one to be next one? If my branch is taken, then my next instruction would be this one, right? And if branch is not taken at that point, my next instruction would be this one. So to mitigate this issue temporarily, processor, let's say this processor, do some prediction. It predicts always non-taken. So prediction is predict always not taken. So in that case, the processor will fetch this instruction into the pipeline, and then it will move on. Now, this guy will be in the write back phase, next clock cycle. So it is writing. This one moves to the mem phase. If needed, it will access data memory. It may not, this instruction won't. This one is now start of the exe phase. So it is start using the ALU. And this one moved into the instruction decode phase. And since it is predict always not taken, this instruction will be picked up, fetched. All right. Now what happens to the next clock cycle is this. This add instruction is done. So this is done. And this guy moved to write back. This guy moved to mem. Now at this point, we know what is the comparison between R1 and R4 and R1. Like this is the comparison point for this guy. So at this clock cycle, now we know the result. Let me come back to that. Let me take care of the other instructions. So at that cycle, this guy will move exe. Okay, ALU. This guy is in the mem. If it is needed, this is in ALU. This one move here. So this guy will move here. And write back is here. Okay. And now instruction fetch, what it will do. Now what it will do something like this. At this point, since it knows that branch is taken, in fact, it's going to be taken, it should pick up this guy because this is jumping back to L. So at this point, at this time point, we know what to fetch. So your processor will fetch this instruction again. Okay. Now, what to do with these two, which was wrongly predicted to be the one? So the processor in a hardware technique, what it does something called replacement of these instruction with no operation and this instruction with no operation. So this is what is injecting a bubble means, like introducing a bubble or injecting a bubble into the pipeline means. You replace that with a no operation means it will not do anything after that point onwards. Okay, so the corresponding resources will be inactive, it is inaccessed and stuff like that, so that it basically follow through the right track of the program execution. Okay, so I need to copy this guy. Then what happens after these, then this is go out of the execution. This one comes in the write back stage, and this one move to mem, no operation, and I move to RDRFA. So since they are NOP, let me decommission those resource access. And now it is reading back this guy. And it will now fetch this instruction. Next one. This is unambiguous. We can fetch it. This instruction again. And then on the next cycle, what will happen? This is done. Okay. And this NOP will move here. This NOP will move here. This will be in the exe. So your exe will start occupying this one. Okay, this guy will move to RF, and this instruction will be fetched. Okay, next cycle, this is gone. This move to the right back. This goes here. This goes here. So this is ALU. This goes ALU. This one goes to RF. And now at this point again, the dilemma comes in, right? Which one to predict? But remember, our prediction is always not taken. So no matter what, even if we know at this point this is going to fail, we'll still predict to fetch this guy over here. And then next clock cycle, this is done. This one moved to right back. This one moved to mem. This one goes to exe. This one goes to fetch. And this one is fetched. Okay, now see, there is this potential bubble again, right? So after this clock, definitely what would happen is this guy will go and it's being done. That's fine. This goes in the right back. This goes in the mems. This goes in the exe. This goes into the instruction decode register fetch. And at this point, we know definitely this instruction needs to be fetched in. So we fetch in that one. And we already know this has to be, these are the wrong instruction fetch. So they are replaced with NOP. They are replaced with NOP. So this is how the control hazard is resolved during the runtime. Question?
Will we have to implement this in project 3?
No.
Okay, thank you.
No, this is project 2 will be still the simple processor as in, sorry, project 3 is a simple processor as a project 2. Difference is that this data processing part will be implementing at the get level with the get level description, no more behavior level there. Okay. Other questions? Yes, no. Okay, let's see. Okay. Okay, why don't we have a pop quiz? Let's see. Just give me 2 minutes to set this up. It will be pop quiz number 7. Okay. Okay. So let's see. Go to your canvas. It's a pop quiz number 7. Let me make sure. Okay, so I'm launching the poll. Once you are ready to enter the password, say yes to this poll. 34 of 40. 36 of 40. I'll wait for a couple of more seconds. 37, 38. 2 more% to go. 39. Anyway, let's mint the poll and share the password. Here you go. Okay, I think for most of you, time is up. Let's take 5 minute break at this point, and when we are back, we'll do some problem solving in group. Okay. Okay, let's get back to our next half of the session. On the quiz, pop quiz score distribution, let me show you what happens to this class. Where is that here? Okay, your high score 100% with average score 53%. This is very concerning. Please make sure to come prepare in the class. That would reflect in your pop quiz as a whole class performance. Anyway, a couple of notes from for your this lecture 15. Number one, remember like this data forwarding, the condition, right? Like when we can do a data forwarding for the data hazard resolve and when we cannot. The principal thumb rule is that your target data must be generated before or at the same time as it is consumed. So in this whole processor system, like you can think of some part like memory or ALU or register file is producing the data, and at some point of time, some stages that data being consumed. For example, like uh, data produced by the instruction, like maybe for example, let me just, why don't I share that part with the example we just did in the class, in this class for your branch prediction. Okay, so in this example, you see that this instruction is generating a new data, right? R2 equals R2 plus 1. So some value is being changed in R2, and that data being consumed at this instruction, right? Add R1, R2, R3. That means this R2 is expecting the updated value of R2 from the previous instruction. So this instruction is my data generator and this instruction is my data consumer. Okay, so we can do the data forwarding if and only if the data is generated already at that point or previous to that point. Just let's do this example once more, just focusing on these two instructions, right? So first we fetch the first instruction. Let me just take them down, take them down, take them down. Oops, delete, delete. Okay, so we fetch it. We fetch this instruction, and now next one, what happens is we are fetching this instruction. Okay, so now what would happen in the next cycle? Just let's just focus on these two. This one will go here, this one will go there. Now at this point, the data R2 being accessed, sorry, the data R2 here, it is being fetched from this guy, but this guy has to be data updated by this one, this instruction, right? So that means at this point, whatever being fetched right from the register file is not the updated value, is not the correct value the program wants to have. So it is wrong, right? Everyone agrees? Any concern question about that part? All right. So we clearly understand at this point the value we fetched from the register file R2 is a wrong value because we need to have an updated value, which is 11 result. from the register file. But that updation won't be done until write back. This instruction goes into the write back stage, right? So now what is happening what will happen at this point in the data hazard? So these guy already generated. Now this point, your result is generated, rated, which is equals 11. And these point, these move to the exe stage. So what at this point, what will happen, instead of using the value picked up from the register file, this generated value will directly fed into this instruction. So this is what the data forward means to resolve the data hazard. And the condition, as I mentioned, is that your data producer must generate that result at that point or the previous cycle as the consumer wanted. Only in that case we can do the data forward. I hope this is now clear to you guys. Any question, let me know. Okay, one more point, just to make sure you got it from our previous discussion, is that, like you have seen that if the branch prediction goes wrong, actually 2 bubble is introduced in the pipeline. That means it is almost like equivalent to a 2 clock cycle stop. Maybe from that pre-recorded lecture video, it might sometimes may appear that I'm talking about 1 clock cycle delay there, but be sure it is 2 clock cycle. Like if branch prediction goes wrong, it causes 2 clock cycle stall or 2 clock cycle delay, at least in that execution point. All right. Question. Okay, now let's do a group problem. Let me see what are the group situation. Breakout rooms. Okay. Okay, all right. Let me give you the problem. Okay, let's talk about this problem now. A 5-stage pipeline-based processor is running on the 1 gigahertz clock, and it's following the branch taken strategy. Branch always taken strategy. Let me just let me just make sure that we got it. Branch always taken strategy. Now it is running a benchmark program with 5 million instructions in total to be executed. And 25%, a quarter of the instructions, are conditional branch instruction. Out of those branch instructions, 65% are not taken. Okay. Now 35% of the rest of the instructions, that is non-conditional branching, they causes a data hazard that cannot be solved using the forwarding. So we have 25% of the instruction of the conditional branch. That means 75% is a non-conditional branching, non-conditional or branching instruction, something that like a data processing instruction you can take. out of on that 75% of instruction, 35% causes data hazard. All right. And out of this 25% branch instruction, 65% branches are not taken. So in that condition, how long will it take to complete this benchmark program? And one more, let me add one more problem there. So this is the first problem.
Professor?
Yes.
The So we should assume that the instructions are also not resolved through reordering?
Yeah, it's not resolved through reordering or anything. Okay. So, and what is the performance gain or loss if prediction was branch always not taken? So this two-part problem, let's do it in a group, and let's take 7, 10, 10, 15 minutes to discuss this problem among your peers. And let me move around some people in the groups. Okay. Okay, I'm opening the groups to all of you, and I'm also opening the share screen so that you guys can go and discuss among yourself.
Professor,
Yes.
did you expect us to figure out just the number of instructions that were saved from not from the for part B, or did you actually want us to like calculate a percentage?
Uh, yeah, part B should be able to use the calculation from the part A.
Yeah, that's
Is
what.
that your question?
Yes.
Okay.
Yeah,
Yeah.
but basically, did you want us to calculate it as a percentage or just as the number of instructions that were saved?
Uh, Actually, I couldn't get your question quite right. Can you repeat, please?
Yeah, did you want, for part B, basically, did you want us to see, note like the difference in the number of instructions? Or did you want us to note it as like a difference in percentage of like how many instructions were not like fewer were executed?
Uh, isn't that like it will be same number of instruction executed no matter what you predict right or wrong. You will fetch extra instruction, but they will be anyway will
Or
be
sorry, I guess clock cycles saved. I'm sorry.
right. So it will be in terms of ratio. Like ultimately, what is the time it took in the A and what would be the time it took in the B scenario. And in the B scenario, you just take a ratio between the execution time of A versus execution time of B. Is that the question? Did I answer? Or
You know, I think I got what I wanted. Thank you.
okay. All right. So let's see. How about group 7? Group 7. Uh, who is group 7? Let's see. Twit, in Nee, and Andrew and Aaron. Have you guys done this problem? Come to a conclusion? Do you want to share?
Sorry, I haven't done it yet.
Okay. Okay. All right. Okay. How about group 4? Yorick, Jason, Mark, Benjamin, group of those.
I'm not sure it's correct, but I can try.
Yeah, please share. Yeah, let's see.
All right, I'll just share screen then. All right, so basically what we did was we concluded, we made a couple of assumptions that we assumed, okay, we have 5 million instructions. And we said, okay, clock cycle equals 1 nanosecond.
Right.
So then afterward, we calculated everything in terms of clock cycles, and we said, okay, these 5 million instructions, where do we get the extensions? First off, we have 25% are conditional,
Okay.
and of which 65% are the branch not taken, or yeah, branch not taken. So they waste 2 clock cycles.
Exactly right.
And then we saw that there was another wasted cause of wastage, and that 35% of other cycles waste. We assumed it was just one cycle in that case.
Right. Correct.
And we assumed that since it's for the other case, it's basically 75% of the 5 million.
Mm-hmm.
So it's 75% of 5 million.
Mm-hmm.
So then we came up with, okay, so it's 5 million plus 4 plus 5 million times 0.25 times 0.65 times 2 plus 5 million times 0.35 times 0.75. And that gives the answer.
Okay, so what was the final answer for A?
Oops, I'm sorry. I am, one sec. I have the number right here. Okay, there we go. The final answer was this.
Okay, so that much nanosecond basically.
Yes.
Mm-hmm. And in terms of millisecond, it will be about 7.937.
Yeah.
5, about that one. Yeah, this seems like correct. One point though, like you added that extra 4 cycle, that's good. Like it's for the accurate result. But you can for 5 million scenario, if you even discard that 4, you will
It'll
get.
still be close enough, right?
Yeah, it don't really matter that for 5 million, with respect to the 5 million, that 4 extra cycle, it doesn't matter. You can safely ignore that in that calculation.
All right.
But this is accurate.
All right.
Okay. How about the part B?
So for part B, it's actually, I kind of regret not saving it, but basically we just did the same thing.
Mm-hmm.
And, pull up the annotate again. And we came to this, this was our result. We concluded that instead of having 0.65%, because now we've switched the, instead of saying that we're following the branch always taken, we're following the branch not taken strategy. So that switches over this 0.65 to the remainder of the branching, conditional branching instructions. And so
Right.
that just changes this number right here.
Exactly.
0.35. And then we come out to this many cycles in total. And then we subtract the difference. We find the difference between the two. And we found out that this many cycles are being saved.
Right. Your approach is correct. This is good. This is perfect. In terms of performance gain and loss, it is always about the ratio between the execution time of, like, you remember that performance equation. It is like px by over px over py is ey over ex. That's the ratio you want to calculate, not the difference between the cycles.
Okay. But even then, it's
That
about
it's
10%, right?
right. It's about 10%. Yeah. Yes. So this is good. This is good. So others, did you guys get it? Or you have any question for Yorick?
Can I stop sharing?
Yeah, sure.
Okay.
Okay, so if we don't have any other question, yeah, I will post that on the whiteboard, the whole solution to you. Don't worry. And then we'll see you on Thursday if you guys don't have any other question. I'll stop by just for a minute to see if there is a question.